In this video, we will learn oxidation and reduction reactions of carboxylic acid derivatives, such as esters, anhydrides, acid chlorides, and amides, not to mention the parent carboxylic acid. We will continue to use the carbonyl grid to organize both what we will learn today and integrate it into our existing knowledge of these functionalities and other carbonyl-containing functional groups such as aldehydes and ketones and their derivatives, alcohols, acetals, etc. Learning goals for today are to be able to predict the products of redox reactions to carboxylic acid derivatives, provide complete curved error mechanisms for these reactions, evaluate the relative reactivity of carboxylic acid derivatives and common reducing agents. Well, clearly we'll be using that ladder of reactivity, right, where acid chlorides are the most reactive and carboxylates are the least reactive acid derivative. And finally, we will propose synthetic pathways involving oxidation and reduction reactions of carbonyl compounds as key steps. Let's get started. As we go along today, we will be adding these reactions to our reaction chart, and you should be keeping one at home yourself as well. We will start today by activating our prior knowledge in a series of review exercises. The first one is to revisit the carbonyl grid, which I will remind you is simply a synthetic tool to think about the transformations between the different carbonyl-containing functional groups as well as functional groups derived from carbonyl-containing functional groups. Take a moment to double check that you've filled in the parts of the grid that we learned in Unit 1 and that were learned in the acyl transfer class. Which squares are those, do you ask? Well, here I have conveniently labeled them for you. So the green squares were learned in Unit 1, and the pink squares were learned in the last class. Be sure that you've filled in all the reagents. Quick warning, some of the reactions we learned in the acyl transfer class are not on this grid, specifically those anhydrides. And today we will learn a few more reactions that will not be on the grid, but will be useful as well. And we'll add them to this little list. Pause now, be sure that you have those squares filled in. Good. In the last class, we did learn about acyl transfer reactions between carboxylic acid derivatives. And acyl transfer reactions involve, as the name suggests, transfer or moving the acyl group from some nucleophile, some species, we'll call it X, to another, which we will call Y. I would ask you to once again pause and review. Give a specific example of an acyl transfer reaction that occurs under each of these three sets of conditions. Be sure that you have your examples written down. Neutral conditions means that there's no catalyst involved in the acyl transfer reaction. Neutral conditions are observed only for the most reactive acid derivatives, which are acid chlorides and acid anhydrides. An example of a reaction to an acid chloride under neutral conditions would be the hydrolysis to generate carboxylic acids. A similar reaction occurs to anhydrides under neutral conditions. Two examples. Bonus. Under basic conditions, an anionic nucleophile is used, which will react with even weakly electrophilic acid derivatives such as esters. This sequence, generating a carboxylic acid from an ester under basic conditions, does require an acidic workup just because the carboxylic acid that would certainly be formed from the addition-elimination mechanism. Nucleophilic addition, nucleophile elimination. The resulting carboxylic acid is immediately deprotonated under strongly basic conditions such as these, as it has a pKa of 5. That carboxylate must be protonated under acidic conditions to generate the final carboxylic acid product. The bottom line is that basic conditions involve an anionic nucleophile attacking the neutral carboxylic acid derivative. The same transformation can be accomplished under acidic conditions, but instead of using a basic catalyst using an anionic nucleophile to attack the neutral ester, an acid catalyst is used, such as sulfuric acid or another strong acid. In the presence of water, this will generate the carboxylic acid product. By protonating the weakly electrophilic ester, a strong electrophile is generated and will be attacked by water, resulting in the carboxylic acid after a series of steps. Now that we've refreshed our memories on some of these specific transformations that can occur under basic, acidic, and for the most reactive acid derivatives under neutral conditions, let's review the mechanisms, the full curved arrow mechanisms for these types of transformations. So go ahead and see if you can sketch out the generic mechanisms for acyl transfer reactions under both acidic and basic conditions. Recall that under basic conditions there are fewer steps, so perhaps you start here. Be sure you've written something down. And if you're feeling really confident, also try to write the generic mechanism for acyl transfer under neutral conditions. Last chance. Here's a screenshot from our last lesson. Let's zoom in. Let's start with basic conditions like I recommended for you at home. I'll walk through this step by step. I know there's a lot written down here. So under basic conditions, the acid derivative is attacked by an anionic strong nucleophile in a nucleophile addition step, generating this tetrahedral intermediate. This tetrahedral intermediate has a good leaving group. In this case, it's going to be X minus. And so it undergoes nucleophile elimination. We have a lone pair push, regenerating the strong carbonyl carbon-oxygen double bond and expelling a good leaving group. We made an analogy to nucleophile additions to aldehydes and ketones, such as the sodium borohydride reduction of an aldehyde shown here. Although the first step is similar, there's a nucleophile addition step to generate a tetrahedral intermediate. There are no good leaving groups. There's hydride, there's carbanions. Those are not good leaving groups. So there is no collapse of the tetrahedral intermediate, simply just protonation to generate the alcohol. So we did discuss the similarities and differences between the reactions of carboxylic acid derivatives, which typically have leaving groups, these X groups, and aldehydes and ketones, which do not. All right, basic catalyst, anionic nucleophile can attack the weakly electrophilic carboxylic acid derivative. However, under acidic conditions, there is a weak nucleophile, such as this generic nucleophile. Thus, the carbonyl must be protonated first. Protonated carbonyl is very electrophilic, and the weak nucleophile, whatever that may be, can add to it in a nucleophile addition step, generating a tetrahedral intermediate that looks similar to the one we observed under basic conditions. We know that the carbonyl-carbon X bond must be broken to yield the product. We've already made the carbonyl-carbon nucleophile bond in the nucleophile addition step. To break the carbonyl-carbon X bond, we must make X a good leaving group. So the proton is transferred from the nucleophile to X, generating HX, which is a good leaving group. After this point, this tetrahedral intermediate can collapse, lone pair push, expelling the good leaving group, generating the protonated carbonyl compound and HX, the leaving group. A final proton transfer step generates the final product. All right, so acidic conditions, proton transfer to make a good electrophile, nucleophile addition, solvent-mediated proton transfer to make a good leaving group, nucleophile elimination, proton transfer to generate the neutral product. We've got this. Now, the last set of conditions are the neutral conditions represented here on the right side of the screen. Neutral conditions, no catalyst, may be encountered when the most reactive carboxylic acid derivatives, acid chlorides, and anhydrides are treated with nucleophiles. These mechanisms are similar to those under basic conditions, but after the initial nucleophile addition step, there's typically a proton transfer reaction and then the nucleophile elimination step. Be sure that you are comfortable with all three generic mechanisms for acyl transfer reactions before moving on. And if you are wondering, well, we're not talking about acyl transfer reactions today, why do we need to worry about this? Well, some of the mechanisms that we're talking about today are quite similar to acyl transfer, and so it is important that we have these patterns in mind. Once you have that, let's move on. The relative reactivity of carboxylic acid derivatives will continue to be important So although you may not be with your group, you can on your own or virtually with a friend, you can list all the carboxylic acid derivatives that you know and then arrange them from most reactive to least reactive. Once you have put all of the carboxylic acid derivatives that you know on this ladder, on this chart, you should add aldehydes, ketones, and aminium ions. How does their relative reactivity relate to carboxylic acid derivatives? Pause and try. Please be sure that you've written something down. We will be coming back to this in just a bit. Speaking of coming back to things, here we are at the carbonyl grid. The carbonyl grid is a synthetic tool. Some of the squares on the carbonyl grid are just one transformation, one set of conditions, while other squares represent multi-step transformations that we may encounter in synthesis problems. The carbonyl grid helps us to prepare for synthesis problems. It's also served as a fun organizing principle for our discussions about the reactions of carboxylic acid derivatives. We can and we have organized the grid or thought about each individual square and classified it as an oxidation, reduction, or neither. So please either get out your copy of the carbonyl grid where you've done this or do it that now. The squares in the pink area of the grid represent oxidation transformations. For example, a primary alcohol with one bond between what will become the carbonyl carbon, which is really the, I won't say it's the only carbon we care about, but we care about that carbon the most. There's one bond between the carbonyl carbon and oxygen in the primary alcohol. Whereas in the ester, transformation represented by this box, the ester contains 1, 2, 3 bonds between the carbonyl carbon and oxygen or a more electronegative atom. And in fact, all of these acid derivatives have 3 bonds between the carbonyl carbon and a more electronegative atom. For the acid, 1, 2, 3. For the acid chloride, 1, 2, 3. For the amide, 1, 2, 3. That is why all of these squares here represent oxidation reactions. Whereas the number of bonds between the carbonyl carbon and oxygen increased in the squares represented in this section of the grid. In this bottom left quadrant, these represent reduction reactions. The number of bonds between the carbonyl carbon and oxygen decreases in these transformations. Labeling the carbonyl carbon, let's take a look at the carboxylic acid being transformed to an aldehyde. The carboxylic acid, carbonyl carbon, contains 3 bonds between carbon and oxygen. Whereas for the aldehyde, way up here, there are 2 bonds between the carbonyl carbon and oxygen. And then the squares that have not been color-coded, we'll color them in orange. Those squares represent neither oxidation nor reduction. This bottom right quadrant is the acyl transfer quadrant that we discussed in the previous lesson. There are no redox occurring in acyl transfer reactions. We can zoom in on that section of the grid. We'll just take a look at one square here. We'll look at acid chloride to carboxylic acid. We'll just point out one more time. There are 3, 1, 2, 3 bonds between the carbonyl carbon and more electronegative atoms in the acid chloride. 1, 2, 3 bonds between the carbonyl carbon and more electronegative atoms in the carboxylic acid. So there is no redox occurring in these transformations. Be sure that you have already made your reaction chart with all of the individual transformations, all of the individual reactions that we learned in the acyl transfer lesson. Once you've done that, you should learn the rules. And what I mean by that is be able to explain these rules down here for thinking about how to make each of these different acid derivatives from the other types of acid derivatives. Memorize more easily because you'll understand what's going on. So learn the rules, be able to explain them, fill in the grid, and then you need to practice, practice, practice. not so much memorizing each square of the grid. You won't need to do that because you'll have already memorized the individual reactions and you'll already have learned the rules. But you can use the grid to make practice problems, and that's really key. That's step 4 here, practice, practice. Yeah, so one more time, you do not need to memorize the squares of the grid. You don't have to do that because you've already memorized the individual reactions and then you learn the rules. And with practice, the squares of the grid will become second nature for you. So let's review what's behind the rules. So anything, acid chloride, ester, amide, and even anhydrides, which are not represented on the grid but behave like acid chlorides, can be turned into carboxylic acids. If we wanted to explain this rule, it is because carboxylic acids are the least reactive acid derivative, because whenever there's a strong nucleophile, which is usually basic, around, it's going to be converted to the carboxylate, which is super electron rich. So carboxylic acids in the form of carboxylates were at the bottom of that reactivity ladder that I asked you to draw just one slide ago. So that means that each of these acid derivatives can be directly converted into a carboxylic acid. Now for acid chlorides, whereas carboxylates are the least reactive, acid chlorides are the most reactive acid derivative. And because of that, we had to do some fancy footwork, and only carboxylic acids can be turned into acid chlorides using a special reagent, thionyl chloride, that converts actually this carbonyl oxygen into a good leaving group, and you're able to replace oxygen with chlorine, generating the acid chloride. And because only carboxylic acids can be converted into acid chlorides, both esters and amides, if they are to be converted to an acid chloride, it must go via the carboxylic acid, meaning whatever you wrote here is going to be the first step in these boxes of the grid, right? Okay, anything can be turned into an ester. That's because esters are also near the bottom of that reactivity ladder. They're one of the least reactive acid derivatives. But often it did involve a catalyst, these transformations. So we can directly, we can convert even an ester to a different ester, right? Transesterification. So all these functional groups can be directly converted to esters. And then finally, the fourth rule, and that's for making amides, is that only acid chlorides can be turned into amides. And this is really because acid chlorides react under neutral conditions. So that makes them special, and acid chlorides or anhydrides can be directly converted into amides using an excess amount of whatever that amine is that you want to end up on the amide. So for all the other functional groups, to make an amide, it must go via, so the first step is making the acid chloride. All right, so you'll want specific reagents in each of your boxes, but I hope refreshing your memory of these rules is helpful as we move forward. All right, let's do it. That was a very long introduction, but we are ready to move on. We're going to start with reduction reactions. So these squares and these squares represent reduction reactions as we already determined just a few moments ago. It would be very helpful if you would pause and determine which bonds are made and broken in these reduction transformations. You should also fill in the reagents for these transformations here, from aldehyde to primary alcohol, from ketone to secondary alcohol. You already know these reagents. These transformations from aldehyde to primary alcohol or ketone to secondary alcohol can be conducted in two ways. The first is with sodium borohydride in the presence of an alcohol or water. Sodium borohydride delivers the hydride. This bond is made in a nucleophile addition step. The alcohol delivers the proton for oxygen. This transformation can also be accomplished with a stronger reducing agent, lithium aluminum hydride, but the proton source must be introduced in a separate step. Since lithium aluminum hydride is a stronger reducing agent, it provides a more basic type form of hydride, and it is incompatible with water or alcohols. It will just react with the water. So the proton must be introduced in a separate step. So that answers the question of these two boxes. Let's take a look now at what bonds are made and broken for this quadrant here. We're just going to look at one square together. You can do the rest on your own. We'll look at this square. So this square represents acid chloride to primary alcohol. Thinking about what bonds are made and broken, we can see that the carbon-chlorine bond is broken between the carbonyl carbon and chloride. And if we had to predict, I bet this leaves in a nucleophile elimination step from some tetrahedral intermediate. And since we're making these bonds to hydride, I bet that's what the tetrahedral intermediate looks like. So I might even predict this aldehyde as an intermediate in this transformation, and I currently know nothing about it. I've never learned about it before. So this bond between carbon and chlorine needs to break. These two bonds between carbon and hydride are made, and then the OH is made. OH is probably made in protonation, just like it was in these reactions of aldehydes and ketones above. And the bonds to hydride, well, they're probably made in a nucleophile addition step. We can predict some hydride donor adds hydride in a nucleophile addition, generates the tetrahedral intermediate we already predicted. That collapses in a nucleophile elimination, generates this intermediate. And now we've made one of the carbon-hydrogen bonds. What could happen next? Oh, hydride could add again, generating another tetrahedral intermediate. Wow, this looks a lot like this. And then what's left to happen? Protonation. Might that proton source be? Or perhaps it's an acid workup, and that would generate the final product, which I don't have room to redraw, but it's right here. We can't buy a bottle of hydride, so what reagent do you think might deliver this? Yeah, well, we currently know two reducing agents. We know lithium aluminum hydride, or LAH, and we know sodium borohydride. So perhaps one or both of them, or maybe some other reducing reagent, is capable of performing this transformation. I have one more question for you to think about before we actually learn these reactions in this lower left quadrant, which is adding hydride the only way to reduce a acid chloride, for example, or any of these functional groups in this quadrant? What do you think about this question? Well, a follow-up was adding hydride the only way to reduce aldehydes and ketones? Were there other ways to reduce aldehydes and ketones? Now, there's another transformation that you know on this grid, which is also a reduction. So it's this one right here, hi, in green, from aldehyde to secondary alcohol. So how is that transformation affected? Let's write that out down here. This reaction does represent a net reduction because the number of bonds between the carbonyl carbon and oxygen decreases. 2 to 1. However, this time a carbon-carbon bond was made, and there's a protonation step. We know that carbon-carbon bonds are made between carbonyl carbons and carbanions, such as Grignard reagents, which are quite reactive like LAH, so the proton source must come in a separate workup step. Good. We reminded ourselves that aldehydes and ketones were reduced with hydride donors and carbanions. So perhaps acid chlorides and carboxylic acid derivatives will be reduced with these two types of reagents as well. So this box in purple that we already discussed, it represents what we think happens when an acid chloride is treated with some sort of hydride donor, perhaps the two that we already know. But now that we've refreshed our memory that carbanions are also reductants, let's take a moment and just predict what might happen if an acid chloride, just piggybacking on that example that we were discussing for hydride here, purple square, so piggybacking on that example. What would happen if an acid chloride was treated with a Grignard reagent? Okay, I'm not going to fill this in on video. You're going to try, make an analogy to what we wrote out for hydride here. So make an analogy, try it yourself, and then you are ready to move on.